So when we talk about modeling with exponential and logarithmic functions, what we're really talking about is using these types of equations to help model some real life phenomena. And we did one a couple classes ago where we had the temperature in degrees of a cup of coffee. And we wanted to figure out after how many minutes would the temperature be 100 degrees. And we solved it graphically before by graphing y equals 100 and then y equals the exponential and seeing where they cross. If we want to solve it algebraically, though, what we're going to be talking about doing here is we're going to say, well, since the temperature is 100, that's our output. So if the temperature is 100, when does the t value give us that input, or that output? So we're solving this equation. That's a horrible looking E. Ugh. Hey, so we're just going to balance that equation. Let's subtract 70 from both sides. And that's going to give us 30 plus 90 e to the negative 0.01 t. Whoop. There we go. We'll divide both sides by 90. So we're going to get 30 divided by 90, which is 1/3, equals e to the negative 0.1 t. And now we got to get rid of that exponential function, so we'll take the log of both sides. Since we're in e, I'm going to use the natural log. So I'll do the natural log of 1/3 equals, bringing my exponent down, negative 0.1 times t times the natural log of e. But we know the natural log of e goes to 1. So then what we're really getting is that the natural log of 1/3 is just equal to negative 0.1 t. So that means our value of t is going to be whatever the log of 1/3 is, divided by negative 0.1. And I think if we go to our calculator and hit that, we're going to get about 10.986 minutes. And if you remember when we did this graphically, an answer of 11 minutes seemed to be pretty good. And we got 11 minutes again, so it seems like we're on the right track. Pretty neat. Well, here's another one that you can try if you'd like. The radius of a fungus on a tree and an equation to model it. So first, see if you can write down the radius where the fungus was initially observed. Yeah, so we know that means we're in t equals 0. So when t equals 0, our exponent is 0. So 2.4 to the 0 power is 1. So that means the radius is 5 centimeters. And now we're told after 4 days the radius is 8. See if you can take a minute and find the value of k. All right, so what we're doing is we're solving 8 equals 5 times 2.4 to the 4k. There's the equation that we're going to solve. So let's divide by 5 and get 8 over 5 equals 2.4 to the 4k. And now let's take the log of both sides to get that exponent down. And again, I like to do natural log. So I'll do the natural log of 8/5 equals 4k times the natural log of 2.4. And the natural log of 2.4 is a number. The 4 is a number being multiplied by k. So my value of k is going to be whatever the natural log of 8/5 is, all divided by 4 times the natural log of 2.4. Hey, so be careful going to your calculator on that. Make sure that maybe this denominator goes in parentheses to ensure that you get the right answer. And I think if we solve for k in this one, we're going to get k is about 0.134241, a whole bunch of numbers. So what if we use k going forward as 0.134? We'll go 3 sig figs on that. So now that we know k, can you figure out after how many days will it first be greater than 10? Give this one a shot on your own. I'll wait for you. All right, so like before, we're going to plug in 10 for our output. And we get 5 times 2.4. And now our k value is 0.134 times t. And we're solving that equation. Now, one thing to notice is that the initial radius was 5. We want it to be greater than 10. So the idea here is that we are doubling. So because we're doubling, when we divide by 5 on both sides, we get 2 equals 2.4 to this exponent. So now when we solve this, we're going to take maybe the natural log of both sides. ln of 2. And then we get 0.134 times t times the natural log of 2.4. And as we saw before, we can just divide everything out and leave the t by itself. So t is going to be the natural log of 2 divided by 0.134 times the log of 2.4. And when we do this, I believe we get about 5.908 and a bunch of numbers. So let's say after 6 days is where the first time it would be greater than 10 centimeters. Pretty neat with that doubling there, huh? All right. Well, one of the most common situations here that we use for these exponential functions is this idea of like compound interest. We're making our money work for us. So in this compound interest question, or this formula, FV is our future value, PV is the present value, R is going to be the annual rate of interest, K is going to be how many times we compound the interest in a year, and N is going to be the number of years that we are keeping our money in the bank. So my buddy Kieran invests $500 in a fund. He's earning 3.2 interest per year, compounded quarterly. Kieran, let me know where you're investing. I love that idea. So great questions. How much money do we have after 3 years? Might need a little bit of room, so I'm going to slide Emma's idea. I'm not going to slide Emma's anywhere. Okay, we're just going to leave it there for a minute. So let's see. If we plug in our values, we're looking for the future value. So we're going to say FV equals. The present value of the money is $500. 1 plus 3.2% interest over 100 times 4, because it's compounded quarterly, which is 4 times a year. And we're going to do that for 3 years. So this is an expression that can go right into our calculator. So when we do that, I think we got our calculators to give us about 550.169 or so. So what if we say he makes about $550? He's made $50 in 3 years. Not too bad. So Emma hears about this and she goes, this is great. I'm going to invest with Kieran. So how many years is it going to take Emma to double her money? Take a minute, think about it. Oh, are you back going to ask me about, hey, how much money did Emma start with? Okay, the answer is you don't need to know it. What? Well, let's do this. Let's say the amount that Emma invests is going to be like some value A. She wants to double her money, so it's going to get to 2A. Watch what I'm going to do here. I'm going to plug in that future value, 2A. The present value is A. And I know you're saying, wait, there's no numbers there. You don't need numbers if you know what's going on. Check this out. Now I'm going to do my 1 plus 3.2 over 100 times 4 to the 4t power. And when we solve this equation for t, the first thing we're going to do is going to be divide both sides by a. And look what happens when we do that. We're just left with 2 equals this thing in parentheses, 1 plus 3.2 over 400 times 4t. Yeah, doubling just puts a 2 there. Tripling puts a 3 there. It doesn't matter how much you start with. The beauty of mathematics. Ah, love it. Well, let's take some logs. I think this decimal in parentheses turned out to be 1.008. So the equation really becomes 2 equals 1.008 to the 4t. And we've solved equations like this a lot so far. So now we're going to take our natural log of both sides, ln of 2 equals 4t times the ln of 1.008. We do a little bit of division. So t equals the natural log of 2 divided by 4 times the natural log of 1.008. And I just want to pause for a second here and say, so when you double it, you don't really even need to solve an equation. If you know you're going to double your money, it's the natural log of 2 divided by how many compounding periods times the natural log of your percentage calculation, your rate of change. Not too bad. But when we go to our calculator, I think we get t is about 21.74 or so. So Emma's probably going to wait 22 years to double her money. So it'll take a long time, but hey, it might be well worth it. All right, here's a good one. It's so good that I got to give it to you in class. So we'll leave the temptation for that for later. And maybe we'll close up this modeling experiment with cooking the perfect roast. You're going to invite me over for dinner and you're going to impress me with your culinary skills as well as your mathematical abilities. So what we're going to do is we're going to use what's called Newton's law of heating. Newton's law of heating says that the rate that an object heats or cools is an exponential relationship with a base of E. It's pretty cool. So notice that T of S is our surrounding temperature. That's like the room temperature or the temperature of maybe the oven. T of 0 is the initial temperature of the object. So at 3 o'clock, we're going to put this roast in a 350-degree oven. Right now, it's 40 degrees, that roast, because it just came out of the fridge. You throw some seasoning on it, you throw it on a pan, you throw the pan in the oven. After 2 hours, you stick the meat thermometer in, and the roast is now 125 degrees. And we want to cook it so it's safe, so we're going to raise its internal temperature to 165. What time is that? Hey, pause this. See if you can figure it out. All right, so I'm going to make some substitutions in this equation here. So we know our surrounding temperature is the temperature of the oven. So that's going to be 350 degrees. So maybe our function is going to be 350 plus, and this thing in parentheses is the difference between the initial temperature and the surrounding temperature. So it's going to be 40 minus 350 times e to the negative kt. And k is going to be this constant that we need to find first. So let's find that constant by doing this part of it right here. We know after 2 hours it's 125 degrees. So I'm first going to solve 125 equals 350. And I think if I do 40 minus 350, I get a negative 310 e to the negative kt. Oops, and I know t also. T is 2. Okay, so let's solve that equation. If I move that 350 over by subtracting it, I get negative 225. We'll divide both sides by negative 310. So that negative divided by a negative is going to become a positive value. So I get 225 over 310 equals e to the negative 2k. Let's start natural logging things. So the natural log of 225 over 310 is equal to negative 2k times the natural log of e. We've seen this before. We know the natural log of e goes to 1. We're going to divide both sides by 2. So k is equal to the natural log of 225 over 310 divided by negative 2. Maybe we want to write that as negative 1/2 times the natural log of 225 over 310. Is that okay? So instead of dividing by 2, I'm multiplying by 1/2 and I pull that negative out. Pretty neat. All righty. And I think when we go to our calculator and we figure out what the value of k is, let's extend the page a little bit. We get k to be something like 0.160235. So what if we use k in this case as 0.16? So let's go back now and figure out when will the temperature be 165. So we'll solve 165 equals 350 minus 310 e, and now we know that our k value, remember, is negative 0.16, and we'll solve this equation for t. So we go the same way. If we subtract our 350, I think we get negative 185. We divide by 310. We're going to take natural logs. You guys got the hang of that right now. So I get 185 over 310, which is equal to e to the negative 0.16t. We go a natural logging. So the ln of both sides, if I take my natural log, it becomes negative 0.16t times the natural log of e, that's going to be 1. So we're going to get that t is equal to this natural log here on the left side divided by negative 0.16. And when we throw that into our calculator, we get that t is equal to about 3.2263 and so on. And if we take this decimal, this 0.2263, because that's how many minutes, but do you really know how long that's really hours. Do you really know how long 3.2263 blah, blah, blah hours is? So if I multiply that number by 60, I get about 13 or so minutes. So you want to know when it's done? It's going to be done in 3 hours and about 14 minutes. That's when it's going to be primed. But then again, you got to take it out, you got to let it rest for like 15 minutes, let the juices absorb and all that good stuff. Hey, this was great stuff. It made me hungry. I got to go get something to eat.